we're going to talk a little bit about ion formation and some properties that happen, periodic properties that happen based on the position of atoms on the periodic table. Sorry, got to bring my pointer back up. I'm never going to remember to do that. So ion formation can be predicted pretty well by the element's location on the periodic table. So the atoms form ions will result in an electron configuration that is the same as that of the nearest noble gas, is what they're generally going to try to do if they're going to form an ion. So metals, going back over the ones we just looked at, alkali metals are group 1A, that's that first column. They're going to form +1 cations. The alkali earth metals are going to form +2 cations. The transition, intertransition, and p-block metals form a variety of charged cations, and these will not always match a noble gas notation. So they can be one, but they're not always going to be the noble gas notation when you start dealing with transition metals. Alkali metals and alkali earth metals, though, are going to always match the noble gas notation once they've become ions. I went too far. Then you have nonmetals. These are going to form anions, negatively charged atoms. Halogens, that'll be the group right before the noble gases, are going to form -1 anions. Your other nonmetals are going to form a variety of charged anions, but the most common formation will be gaining enough electrons to reach the noble gas notation. So if you're ever not sure, unless you're given specific information otherwise, assume your nonmetal, when it forms a charged anion, is going to gain enough electrons that it's able to go from wherever it is to the noble gas that's closest to it to the right. So let's look at some examples. So we're going to look at, if we give us a configuration, like an ion, what its electron configuration would be. So I'm first going to work lithium plus by myself and let you watch, and then you're going to try B and C, and then I'll go over it. For each of these, what I'm going to start with is I'm going to start with what is the configuration when we're not doing the ion. So what is lithium on its own? So if I had to do the electron configuration for lithium, I would say that lithium was 1s2, 2s1. You could also say helium 2s1. That would be fine. You'll notice lithium here now is lithium plus. So for lithium plus, the plus sign means we lost an electron. We need to take one away. So lithium plus is just going to be 1s2. And that would be my answer for lithium plus. I would also accept that lithium plus is helium, since that's noble gas configuration. But if it's a multiple choice question, you need to be able to recognize that both of those are valid answers. So I want you to try B and C, pause the video, and give them a try. Okay, let's look at those now. So B, let's look at oxygen on its own. Oxygen on its own is going to be helium, because I'm going to practice my noble gas notation, 2s2, 2p4. Now helium had a 2 minus. That means it gained 2 electrons. So for O2 minus, we'll have helium, 2s2, 2p6. Note that I would also accept if it were a free response type question. You could also just see neon. Since neon would have 10 electrons, it would also have that configuration, but this is more likely to be what you would see. Then we have magnesium, Mg. Before we go to Mg2+, so magnesium was 12 electrons. So that was neon, and then 3s2. So for Mg2+, since it lost 2 electrons, it would just be neon. You might also see it as 1s2, 2s2, 2p6. Both of these would be valid answers. You should recognize either of them for the configuration of magnesium 2+. So what you need to notice here is that if it's a cation, it's going to lose some of its valence electrons. If it's an anion, it's going to gain some extra electrons. So you should be able to write a configuration for an atom on its own or for its ion. To be able to figure out the ion, you need to start with what was the electron configuration before it gained or lost electrons, and then add or subtract appropriately to match the charge on the ion. So that's with our configuration of ions. Let's look at some stuff with periodic trends now to help us figure out some of the information we can learn from where things are on the periodic table. So the first trend we're going to talk about is the effective nuclear charge and atomic radii. These are both related to the size of our atom. So to start with, there are several methods for measuring the radius of an atom. And they all give you slightly different numbers. So this is what can be tricky about it, is there's different ways to actually measure how big our atom is. So for example, we can talk about the van der Waals radius. This has to do with the size of the atom when it's not bonded towards other atoms. You also have a covalent radius. What about if I were to take the atom and bond it to something else? How close does it tend to be to things? So the atomic radius that you'll see when you look up a measurement like this is the average radius of the atom based on measuring a large number of elements and compounds containing this element, with understanding that if you put this atom in different circumstances, connected to different atoms, it may change slightly how large or small the atom is. But this can give us a good overall average to compare it to other atoms, to say, is this atom bigger or smaller when compared to another atom in general? So to help understand the size of this atom, it can help to talk about a concept we call effective nuclear charge. So the effective nuclear charge is the net positive charge that is attracting a particular electron. So as you might imagine, if a positive charge is pulling an electron in, it'll help make the atom smaller. So what happens is that core electrons effectively shield electrons in the outermost principal energy level from the nuclear charge of the nucleus. So those electrons in the middle, they're closer to the nucleus, and they're positive charges. So they're negative charges. So the negative charges that are closer to the nucleus get in the way of the electrons on the outside seeing all the protons in the middle. So the outermost electrons in the valence shell do not shield each other effectively. So we don't have to worry about the ones at the end don't try to shield themselves. So we can write this as an equation where Z represents the nuclear charge and S is the number of electrons in lower energy levels, so the core electrons. So remember, number of electrons in lower energy level, this is a way of saying the core electrons. So electrons in the same energy level contribute to screening, but since their contribution is so small, we're not going to calculate it as part of it. So only worry about core electrons for your valence electrons, which is when we're going to come up. So Z effective is what does each an electron at the valence effectively feel. So you take the nuclear charge in the middle and you subtract the number of core electrons. Now this is a bunch of words. Let's look at an example that may make it a little easier to see. So we take the element lithium. Lithium has 3 protons in the middle. Those 3 protons on their own would pull the electrons in fairly close. But lithium has 2 core electrons. Those are in the 1s orbital. It has 1 valence 2s electron. That 2s electron feels like there's a nucleus that's the equivalent of only having 1 proton because those 2 electrons in the core shield the nucleus. They make it so that outer electron can't feel the full positive charge because there's some negative charge in the way. So think of it as having an effective nuclear charge of +1. And this will help us understand some of the patterns when it comes to size as we look at this. So what is the periodic trend as it relates to atomic radius and effective nuclear charge? So the atomic radius decreases across a period going left to right. This means that as you add electrons to the same valence shell, the effective nuclear charge increases. So for example, lithium had only 1 valence electron. It only felt like there was 1 proton in the nucleus. But if you go over 1 more from lithium, you will get to the element magnesium's down below. You'll get to beryllium. I was going down the wrong period. So if you go to beryllium, it's going to feel like there are 2 protons in the middle. So that means it's going to have a stronger pull. And so as you go left to right across the periodic table, you're going to get smaller and smaller and smaller. And this is because the valence shell gets held closer together because the nucleus gets stronger. On the other hand, as you go down the periodic table, your valence shell is going to get further away from the nucleus, and so it's going to increase in size. So effectively, if you think of your periodic table, what happens is the bottom left is really big and the top right is really small. So you can think of it as having a trajectory that looks like this, where these are the large elements and these are the small elements when it comes to size. So as you go left to right makes it smaller, so right to left would make it bigger. So if we've got our whole periodic table, this way is going to be where our larger elements are. And as we go down, we're going to get bigger. And then again, that pattern still holds, so if we go both left and down, we're going to get our largest, will be our biggest. And so this actually matches up here, right? Cesium right here is the largest element we have on our periodic table, and that's going to occur at 55, so that'll be down to the far left. Now, francium, if you look at your periodic table, would actually be larger. The only reason they don't have it on this picture here likely is because francium is going to be fairly unstable, and while it can exist, it's not going to exist by itself very easily. But no, as you keep doing the pattern, francium will effectively be your largest element when it does exist on its own, whereas fluorine, it's going to be in the top right of your periodic table, it's going to be really tiny. Note that when we talk about these trends, there are a number of them. We're going to look at 4 or 5 trends. We tend to stick to the non-noble gases. We don't talk about the noble gases a whole lot. They can sometimes, their trend can be a little wonky with it, but in the case of size, they're about the same size. They're a tiny bit smaller than the element right next to them, as you may notice. The other thing to notice here is I'm not going to ask you to deal with the trends when you're dealing with the transition elements because they're not consistent. You'll notice they get smaller than bigger than smaller sometimes. So this is why we talk about main group elements versus transition elements. The main group elements are very predictable in their trends. So we will tend to focus on our trends talking about those. Whereas the periodic elements, they're not perfect. They sometimes have some places where they don't go exactly with the trend that we're suggesting. So, what do we need to know? Our atoms in the same group increase in size as you go down the column. Atomic radius decreases as you go across a period. So from left to right. So what that means is, again, just think of that picture I drew on the last slide, where it gets really big towards the bottom left, that's where the big is, and tiny towards the top right, that's where it's tiny, or small. Atomic radius of the transition metals is roughly the same. I'm not going to ask you to worry. I'm not going to ask you to do the sizes with that part, so don't worry about dealing with those. I won't be asking about the sizes of your transition metals. So I want you to try these 3. Try to find these elements on your periodic table and figure out which is going to be the largest of them. So pause it and give it a try. It's good practice also in finding elements on your periodic table. Okay, so first, nitrogen or fluorine. They're both in the same period. Nitrogen is to the left. So remember, when you go to the right, you get small. So nitrogen is going to be larger than fluorine because nitrogen is to the left of it. Now, K and Na. If you find those, they're both in the same group. So as you go down, you get bigger. So potassium, K, is going to be larger than sodium. And then finally, you have phosphorus or germanium. Well, it gets big as it goes to the bottom and to the left. So germanium is both one left of phosphorus and one below. So germanium is going to be bigger. So note with these trends make easy to ask questions. They're multiple choice. They're hopefully reasonably quick. So they're good things to ask about. So this is where we're going to end for this week with what I'm doing. We do have a few more trends that we'll be covering in another video that I'll be looking at next week, assuming you're watching this in 2020. And maybe in another year we might change the order a little bit. But this is where we're stopping for this week in my current plan. There are a few more trends, and that'll finish up the chapter. We're just about done with it.